So we are treating this material in a different way than most textbook authors treat this material. What the plan is for talking about flux integrals, flux density, and the divergence theorem is that we're going to talk about these ideas all together as a single unified set of topics rather than separating them out. And the way that we're going to do that is we're going to focus today on how to talk about flux integrals, which is the sort of perpendicular notion to that of circulation. So instead of looking at how a vector field flows along a parametrized curve, we want to look now at how a vector field flows across a parametrized curve. And so it really is kind of a perpendicular idea. And so we're going to talk about these ideas today in just a two-dimensional context. So for a two-dimensional vector field in the xy plane and a curve drawn in the xy plane, how can we think about these ideas of flux integrals, flux density, and then what does the divergence theorem actually tell us? And then in our next class and the class after that is when we're going to lever up into the three-dimensional context. And doing that just requires that we take our xy plane, which is nice and flat, and replace it by some surface which might not be flat anymore inside of three-dimensional space, and consider the flux of a vector field through that piece of three-dimensional surface. And so surface integration is going to come back to us. We already saw examples of surface integration when we did our section on surface area a while back. And so now when we go into tomorrow's class and the class after, which is the last one for the semester, we're going to look at how to compute flux through a surface and then flux through a closed surface. And along the way, we're going to find out that actually the flux through a patch of surface can be computed as a surface integral, but actually there is a Green's theorem-like result that can take that surface integral and turn it into a circulation integral instead. That's called Stokes theorem. And then in the case where we have a closed surface, so like the outside of a sphere or something like that would be an example of a closed surface, then in that case we have something called the divergence theorem, which we're going to get our first taste of today in the two-dimensional context. It also exists in the three-dimensional context in a completely analogous way. So today we talk about all of the two-dimensional flourishes of flux integrals, flux density, and divergence theorem, and then we bring surface integrals to the party tomorrow and the class after that, in which case we get a chance to see the divergence theorem work in 3 dimensions, but then also get a new tool, the last new tool for the semester, called Stokes theorem, that can let us compute the flux through a surface that's not necessarily a closed surface, and by converting it into a circulation integral instead, which is always a good trade if we can make it.